Welcome, everyone. Ready to dive into the world of fluorovium.
Element 114, right?
Yep, fluorovium, element 114. And, just to set the scene, it's synthetic.
So not just walking around finding it then.
Exactly. It doesn't exist naturally. Got to make it in a lab.
Super heavy, extremely radioactive. Sounds fun.
Oh, it is. Trust me. So we're going to unpack all that.
Yeah.
How it's made, what we think it's like.
Yeah.
All based on what's on, the Wikipedia page for fluorovium.
Well, good thing Wikipedia is pretty reliable most of the time.
For sure. So fluorovium, it's way at the edge of the periodic table. Really pushes what we know about chemistry.
Air frontier, huh?
Yeah, you could say that. Okay, so first things first, how do they even make an element like this? It's not like mixing stuff in a beaker.
Nah, nothing that simple. Think particle accelerators, huge, powerful things.
I'm vaguely picturing that, yeah.
It's like you're trying to hit one atom with another atom, incredibly tiny target.
Talk about needing good aim.
You're smashing these nuclei together, lighter ones into heavy ones, hoping they fuse. That's how you get super heavy elements.
So for fluorovium specifically, what's the recipe?
Plutonium-244, that's your starting point.
Okay.
And you bombard that with calcium-48 nuclei. Sounds wild, right?
Kinda, yeah. And then, boom, fluorovium.
Well, if you're lucky, a few atoms pop out. But it's not over then. Not even close.
Wait, making it is only step one. I figured that was the hard part.
Oh, it's unstable, fluorovium. Like, really unstable. Most of its forms, they decay in seconds.
Seconds? Why?
Yeah, so back in '98, scientists thought they'd got it.
Uh-huh.
They saw one atom lasted 30.4 seconds, then poof, gone.
Talk about fleeting.
And later, people were like, wait, was that even fluorovium?
So how'd they know for sure they'd made it if the first time was so iffy?
Persistence. They did the experiment again in '99, got 2 atoms this time.
2 whole atoms. Lucky them.
They decayed a bit differently, these ones. Half-life wasn't the same.
Uh-huh. So that helped confirm it.
Plus more experiments after that, yeah. So fluorovium is real, just super hard to hold on to.
Okay. So it exists, it's heavy, disappears fast. But what's its personality like, chemically speaking?
$1,000,000 question.
Yeah.
And the answer is, we're still working on it.
Gotta love science. Never a dull moment.
Right. So early experiments, like back in the 2000s, they thought maybe it acted like a noble gas, very unreactive, standoffish.
Interesting.
But later on, research suggested it's more metallic.
Hold on. A metallic noble gas. Isn't that a contradiction?
Yeah, it seems weird, right? But here's the thing. It's all down to what we call relativistic effects.
Ooh, sounds complicated.
In super heavy elements, like fluorovium, the electrons are zooming around the nucleus ridiculously fast.
Like how fast?
Close to the speed of light, fast.
Okay, that's fast.
And that messes with things. Their mass gets bigger, the orbitals change shape.
Orbitals, like where the electrons hang out.
Yep, exactly. So basically, it's hard to predict how fluorovium behaves. Those speeding electrons throw a wrench in the works.
So mapping out its chemistry. Gotta be tricky if the rules are different.
Oh, it's a challenge for sure. But that's what makes it so exciting, you know?
I can see that. Like, it could have totally new properties, unlike anything we've seen before.
Could blur the lines between metals and noble gases, yeah.
Fluorovium, the chemical chameleon. But honestly, why should we care?
Good point, right. It's here for a second, then gone, and even then, we barely know what it is.
Exactly.
But here's the thing. When we push the boundaries of science like this, explore these extreme elements, it often leads to amazing stuff, things we never expected, new technologies.
Okay, I can get behind that. Like, what kind of practical things could come from studying something as weird as fluorovium?
Think about radioactivity back when it was discovered.
Seemed pretty out there, right?
Totally. Nobody knew it changed medicine, energy, all that.
True.
Fluorovium, these super heavy elements, they could be the same. Open doors you can't even imagine yet.
So it's like a gateway to the unknown.
Exactly. Who knows what secrets it holds? And there's more to the story, too. Remember you mentioned the island of stability?
Oh, yeah? That sounds intriguing.
That adds another whole layer of mystery to fluorovium.
Okay, I'm hooked. Tell me more about this island of stability.
Well, it's this theoretical region on the periodic table. It's this idea, right, that somewhere on the periodic table there's this zone.
A zone.
Yeah, like a region where super heavy elements could actually hang around for a while.
Hang around, meaning?
Not decay so fast, longer half-lives, way longer. See, usually the heavier you get on the table, the more unstable.
Makes sense. More stuff crammed in, more likely to fall apart.
Exactly. It's all about that repulsion, the protons in the nucleus pushing each other away.
Okay, so how does this island or whatever, how's it different?
Well, scientists think there might be these, Magic numbers?
Magic numbers.
Of what? Protons and neutrons. Certain combos, and they make the nucleus extra stable.
Why would that be? I mean, it's not like they're arranging themselves neatly in there, right?
Kind of, actually. They have shells inside the nucleus. Protons and neutrons do.
Whoa, like electrons have shells around it.
Similar idea, yeah. So if you hit those magic numbers, fill the shells just right.
Then it's happy, stable.
Oh, balanced, yeah. Less of that pushing apart feeling.
So where does fluorovium fit in? Is it on this magical island?
At first, they thought so. Specifically, Fluorovium 298, that isotope.
What's special about that one?
114 protons, 184 neutrons. Doubly magic, they called it.
Sounds powerful.
Right. The prediction was it could last for years.
Years. Compared to seconds, that's practically forever. Imagine what you could do with it if you had that much time.
Yeah, the possibilities were huge. But more recent research,
Oh.
it kind of suggests the island center, the most stable spot, might be somewhere else.
Somewhere else. Like, what, did fluorovium get evicted?
Think more like the island shifted a bit on the map.
So, fluorovium 298, not the magic key it seemed.
Maybe not the key, but doesn't mean there aren't other long-lived fluorovium isotopes out there. Just maybe not right smack dab in the middle of the island.
Okay, so there's still hope.
Oh, absolutely. And keep in mind, this whole island thing, it's still theoretical. We're still mapping it out. Every new discovery adds to the picture.
So, back to fluorovium. We know it's hard to make, decays fast. How do you even study something like that? It's like trying to analyze a shooting star in a test tube.
Ha! Great image. It is a challenge, but scientists are clever, you know? They've come up with ways to work with these fleeting elements.
Like what? Spill the secrets.
Well, you make tiny amounts, just a few atoms at a time. Then you gotta be super precise, control everything, temperature, pressure.
Not room for error, huh?
Nope. And then you need detectors, really sensitive ones, to catch the data before it's gone.
It's a race against time, basically.
Exactly. So those early experiments, the ones that hinted at fluorovium acting like a noble gas,
Yeah, remind me, how'd they do those?
they looked at how fluorovium atoms interacted with a gold surface.
Gold. Why gold?
Noble gases, they're the loners of the periodic table, right?
Oh.
Don't react much, even with metals like gold.
Right.
So fluorovium, it kind of did the same. Weak interaction with the gold, didn't want to bond much.
Okay, so like they bounced off each other. Not literally, I guess, but
It's more like their electron clouds are influencing each other, maybe forming super weak bonds. Relativistic effects make it complicated, but the point is, it was a clue that fluorovium might be shy, chemically speaking.
like a super heavy introvert, right?
Something like that. But then, well, the story gets more interesting.
What happened?
Later on, different experiments, especially some done at the GSI in Germany,
Uh-huh.
they started getting different results. Fluorovium seemed more reactive than they thought.
So not so standoffish after all.
Maybe not. And its interactions with gold, they were more typical of a metal.
So which is it? Metal or noble gas? Make up your mind, fluorovium.
Huh, right. Some scientists even think fluorovium, along with its neighbor copernicium, they might be a whole new category.
Ooh, a new category. What's that?
Volatile metals.
Hey, volatile metals. Isn't that like an oxymoron?
It sounds weird, yeah.
Yeah.
But think of it like this. You got your typical metals, solid, shiny, right?
Right.
Then you got your noble gases, all floaty and unreactive.
Okay.
Volatile metals, they're somewhere in between. Maybe liquid, maybe easy to vaporize, but still with some metallic bonding going on.
So like metal that wants to be a gas.
Kind of, yeah. Makes it even trickier to study,
Well,
obviously.
I can imagine. Okay, so fluorovium, this mysterious element, here for a second, then gone. Maybe a new type of matter entirely. What are scientists doing to figure it all out? So much mystery still surrounding fluorovium. What are scientists doing to crack the case, so to speak?
Well, first off, they need more of it. The more atoms they can make, the better they can study it.
Easier said than done, right?
Yeah.
We've talked about how tough it is to create these super heavy elements.
Oh, yeah, it's a huge challenge. That's why they're always looking for new ways to do it, different techniques.
Like what? Tweaking the recipe? Yeah, trying different target nuclei, different projectiles, seeing what works best.
Tinkering with the atom smasher, basically.
Exactly. And some scientists are even thinking about, well, more extreme methods.
Extreme. How extreme are we talking?
Some are looking into using controlled nuclear explosion.
Hold on. Explosions to make elements.
The idea is to reach the energy levels needed, to force those atoms together. It's still very theoretical, but
Sounds a little risky using explosions for science experiments.
it would definitely be high stakes. But the payoff could be huge. Imagine new elements with properties we can't even imagine yet.
A whole new periodic table. Who knows?
Mm.
Okay, so let's say they get more fluorovium, even some that sticks around longer. How do you actually study something that's so rare and so fleeting? It's not like you can just put it in a beaker.
Right. Traditional chemistry's out the window. But they've got these amazing techniques now working at the atomic level.
Okay, I'm picturing tiny tweezers and stuff.
Huh. Kind of. One way is to trap the atoms, like in a vacuum chamber.
Yeah.
Then you hit them with lasers.
Lasers. What do lasers have to do with it?
They excite the electrons in the fluorovium atoms. And when those electrons calm down, go back to their normal state, they give off light.
Okay.
And by analyzing that light very precisely, you can learn about fluorovium's energy levels, its electron structure, like a fingerprint made of light.
So lasers are the key to reading fluorovium's atomic fingerprint.
Pretty much. And that tells you a lot about its chemistry, how it might bond, what kind of compounds it could form, whether it's more like a metal or a noble gas or something totally new.
Amazing how much you can learn from just a few atoms.
It really is. And it's not just about individual atoms either. They're also working on making and studying larger quantities. Well, larger is relative.
How large are we talking?
Nanograms, picograms, tiny amounts. But still, it's progress.
Remind me, how small is a nanogram again?
1/1000th of a gram. A picogram is even tinier, 1/100000th.
Okay, yeah, those are tiny.
But even with those tiny amounts, they can use sensitive techniques, mass spectrometry, chromatography.
Big words.
Basically, ways to separate and analyze different fluorovium isotopes, maybe even see how they react with other stuff.
Like a super high-tech chemistry set.
You got it. And every bit of data gets us closer to understanding fluorovium, what it really is.
You know, what impresses me is the sheer dedication. These scientists are working with something that's almost impossible to study, but they keep pushing forward.
It's true. It's a testament to human curiosity, our drive to understand the universe, even the weirdest parts of it.
So, where do we go from here? What's the big picture goal with fluorovium?
I think it goes beyond just fluorovium itself. It's about understanding all these super heavy elements, what they can do.
Yeah.
Imagine materials with properties we've never seen before. Super strong, super efficient catalysts, new ways to make energy. In a long shot, but the potential is there.
That's exciting to think about. Even if those practical uses are far off, just the knowledge we're gaining is incredible.
Absolutely. It changes how we view the universe, what we think is possible. Maybe one day we'll be talking about fluorovium not in atoms, but in grams, kilos.
Now that would be a game changer. But for now, the journey itself is fascinating. All the research, the clues, the constant pursuit of this elusive element.
It reminds us that there's so much left to discover, even in something as familiar as the periodic table.
Fluorovium, a story of exploration, perseverance, and the power of scientific curiosity. Thanks for joining us for this deep dive, everyone.